Well then, hello everyone, and thanks for showing up for my talk. Today where I'm going to talk about model adequacy in diversification. So I know this is a fairly interdisciplinary crowd to talk to, but I think one thing that we probably all have in common is that we work with models. And we probably all know that models can be really useful, but that a lot of things can also go wrong, and that there's a lot of caveats if we want to be sure that our models tell us what we think they should tell us. And so one thing that we usually do is that we might have different models that model different processes, and we want to find out which one might be going on in creating the data that we're looking at. And we might be able to compare the fits of those models to see which of those fits best. However, knowing the fit of the model, knowing which one is closest to what might be the truth, doesn't really tell us much about how close we actually are. And so that's where model adequacy comes into play. So the goal here overall of my work, which is still preliminary, it's a project where I'm kind of 2/3 in, is to develop a model adequacy approach for diversification models that also allows to pinpoint in which way a model is not adequate for the data that we're trying to analyze. So talking about model adequacy real briefly, often the idea here is that for a model to be adequate to analyze certain data, it needs to be able to kind of depict that data properly. So if we make a very simple example, imagine we're tossing coins and we want to know whether we can use dice to analyze coin toss data. But if we look at the data, we can see that, the coin toss data is pretty much 1 or 2, and the dice roll will be between 1 and 6, and the data will, it looks different. So even if we break out our fancy dice, the dice will never properly create data that looks like coin toss data. So dice, like 6-sided dice, would be a bad model for coin toss data. Now, being a biologist working in macroevolution, what I care about in terms of the model is diversification. And what I mean here is diversification in the sense of lineage diversification. So the dynamics of speciation and extinction. So the main things we're asking ourselves here are questions like, why do some groups have a lot of species and other groups very few? Kind of ask ourselves, how did speciation and extinction vary over time? Because remember, there were times when things died out a bit more and other things originated a bit more. And then, of course, we also wonder, well, what might be things that have influenced these dynamics in diversification? Like the classical example of flowers with nectar spurs that seem to have higher speciation rates than flowers without. And so the way we do this is that we have models that estimate rates of diversification, so of speciation and extinction. What we use for that is we usually have a phylogeny on species level that is like time calibrated, so the length of the branches represents the time since 2 lineages have diverged. Then we usually have some kind of model that can describe a mechanism for the speciation and extinction dynamics and a way to like find out what the best rate estimates for this would be. For example, maximum likelihood, or there's Bayesian approaches. And then depending on what model we're using, we might also incorporate other data that we think might have influenced those rates. That can be things like geography or traits of the organisms or habitat or other kind of ecosystem related things. So people have been using those models quite a lot to answer questions. For example, here someone figured out that was Pyron and Burbrink, that egg-laying squamates have lower speciation and extinction rates than viviparous ones. Or Price et al. Have found that we have higher diversification rates in herbivores than in omnivores than in carnivores. Or McDaniel et al. Found that in moss, hermaphroditic lineages have a higher rate of diversification than dioecious ones. And it actually, those kinds of models can extend into related fields. So Stadler and Bonhoeffer have, for example, adapted a similar kind of model for HIV, where they try to see whether in different clusters of transmission, like in different groups, the rates of transmission are higher or lower. So there's a lot we can do with those models. I'm quickly gonna talk about some of the models that I'm specifically looking at a bit more. And so the simplest model we're thinking about is the constant rate model. So here we do have, for example, a trait that has two states, A and B, and it can switch back and forth between those two states. But the extinction rate mu, where lineages get lost, and the speciation rate lambda, where new lineages split off, are the same between both of them. So there's a constant rate of speciation and extinction, and the trait doesn't really have anything to do with it. That just happens. So now we have state-dependent models as well, where we essentially have the same kind of setup, but actually lineages in state A will have a different rate than lineages in state B. So they could have higher extinction or higher speciation or whatever. And this will, of course, lead to slightly different looking phylogenies. So in this fictional case here, we could imagine that green clades might have slower diversification than purple clades. And then finally, another model that people came up with that is very useful in this case are state-independent models. They still have different groups of rates, but they're not related to the trait. So you see, we still have a green trait state A and a purple trait state B, but the diversification rates are actually different between group 1 and 0, which are independent of the trait. So what that would look like is we still have a slow diversifying clade and a faster diversifying clade, but they don't really match up with the traits. So they're independent. And therefore, we would expect different kinds of trees to come from those. And so now we want to see whether we can find out whether a model is better suited for one or the other. So as I said, especially this trait-dependent model, state-dependent model has been used quite a lot. It's been very popular. So there's a lot of research where people tried out exciting things with these. But as time went by, we discovered more and more issues with them. Just for a few examples, we found issues like, if we only have one clade that changed the trait and it got a higher diversification rate, that doesn't really allow us to say really whether those things are related, because we really just have a sample size of one. We have no replication. Other people have found that you can have trees with a neutral trait that we simulated and know that there is no relation to diversification rates, but the model will still tell us that there is a relation. So they are vulnerable to false positive results under some circumstances. Then other people have devised that they might actually, those methods might not actually be as good as we thought at finding the things that we want, and that we would actually prefer to move towards a more mechanistic and more causal way of looking at it. And last but not least, there's a recent paper which found identifiability issues in general birth death diversification rate, which are underlying these models. And the problem here is that for every solution that a model like this gives us, there exists an infinite number of alternative scenarios which have the same likelihood, so we cannot really tell them apart. So of course that kind of looms over this field now, and we kind of really need to find ways to figure out whether we can rely on the results that we've gotten. And so hopefully model adequacy could help with that, both in a way of finding out whether the result you got under a certain model is adequate, or also whether some of the alternative results that could exist are feasible for this data and whether we should consider them. So model adequacy testing has actually been done already in related fields. So people have used them to test the adequacy of substitution models in tree inference, so to make the tree itself from the genetic data. There have also been approaches to test adequacy in trait evolution models, and as well as in phylogenetic models, again, to make trees. And what is often used here is a posterior predictive simulation approach. And I'm going to show on my own example how that is going to work. So we have an empirical tree that we would like to analyze, and we have a model that models a certain process that we think might be underlying this tree. So what we're doing now is that we are estimating the parameters of that model, of that tree under that model, in a Bayesian way. So we will get a posterior distribution of parameter estimates. Then we will pull parameters from these posterior distributions and simulate a bunch of other trees. So the thought, if you think back on the coin toss example, the thought here will be that if this model is adequate for this empirical data, then these trees should look similar to the initial tree. So what we're doing here is that we have a number of summary statistics which should capture properties of those trees. And we're going to measure them for all of those trees and get a distribution of those. And then we're going to measure the same summary statistics for the empirical tree and see how it compares to the simulations. So if a summary statistics looks like this, where the empirical value falls within the simulated ones, then we would assume that the empirical tree and the simulated trees look the same in that respect. And therefore, the model would be considered adequate. However, if we have a case like this, where the empirical values fall outside of the simulated ones, then we would assume that the simulated tree looks different in a way that the model cannot depict. And so the model would not be adequate to capture those aspects of the empirical data. So I don't want to talk too much about the summary statistics because there are a lot of them and we're trying out a lot of things. But just to give you a rough idea, they're all different measures that try to capture different aspects of branch lengths, trait states, reconstruction of the trait states along the tree, and tree topology, as well as combinations of those. So if we take those three models that I've introduced, and we are trying to use this adequacy testing approach on them. And we would simulate our empirical trees so we know the actual answer under each of these models, and then test the adequacy of all the models against all those trees. What would we expect? So first off, hopefully, we would see that each model is adequate to analyze a tree that was simulated under that same model, right? Everything else would be a bit concerning. Then some models are nested within the others. So for example, the state-dependent model kind of can represent a constant rate process if the two different rates are just the same, because then it's essentially the same model. So we would expect that the more complex models will also be able to adequately depict the trees made under the simpler models. And finally, we'll expect the opposite as well, where the trees that are based on a more complex process cannot be adequately depicted by a too simple model. Okay, so now we run a bunch of examples like that, and we're going to see whether we find what we expect. Ta-da-da. And we kind of don't everywhere. So the interesting bits to look at here are these three cases, where apparently the state-independent model is not adequate for the state-dependent model, and none of these two models are adequate for trees that are evolved under a state-independent process. So what is going on here? Let's start off with this case here. So the idea was that the models are nested. So if we have a tree that was made under a state-dependent model, would be having a higher rate, and we feed this tree to the independent model, we would possibly expect that the state-independent model will catch those two different rate categories, right? It would figure out that, oh, this is a clade with a high rate, this is a clade with a low rate. And then basically the model doesn't consider the traits, but you know, the categories and the traits just kind of align, and therefore the model works out. Now that will be the case, but the problem is if we take those parameter estimates now and feed it back to that model to make the simulations, there is nothing in the model that describes how those 0 and 1 rate categories align with the trait. So really, if we simulate under this data again, we are getting trees that kind of look similar, but there is no relation of the trait and the rate differences. So if we then compare those trees, we can see that they're different in that way. And so there will be the occasional tree here that will look like this, where the traits and the rate categories align, but those will just be random. And actually, if we, so these are diagrams of diversification rate under the different trait states. So if we have state-independent trees and we run them under the state-dependent model, we actually find that every once in a while, we get a result that says, oh, this is trait dependent because just by chance the trait and the rate category is aligned. But most of the time they will not. So that's what's behind this case here. So we realize these models are not really nested actually. Now what's going on here? Because we would actually assume that this should create, along the same logic, this should create a tree that is very different from these ones. Now here we're getting to a little cautionary tale. And that is, the whole thing is not going to work if our rate inference didn't work out properly. So these are the rates that we've put in when coming up with our example trees, with a bunch of lineages associated with one trait that have low rates and another bunch with high rates. Now, if we estimated these, we do kind of get peaks where we expected the peaks at the same rates, but for some reason, the analysis couldn't really figure out the limits of the lower rate and inferred all these possible, this whole rate gradient here. So obviously, if we take, if we take rates from this distribution, those rates are not going to be in two different classes. And so we end up with trees where we do have like trait dependence, or trees where we have kind of the same rates. So we end up with a huge mush of trees, and therefore the distributions of the summary statistics are just going to overlap with whatever. So definitely there will need to be some kind of advice in the final product we're making here that says you may want to check for the properness of your rate estimates. Now, where else are we trying to go from here? So I've kind of talked about the summary statistics a little bit at this point, but once we figured out the other problems I just mentioned, we're trying to go a lot more into that. So obviously, I've just kind of shown you a summary of like, did the tests say that it's adequate or not? But different summary statistics don't always agree on it. And so some of them we kind of know, oh, so the blue and the yellow model are models where we have trait dependence. Gray is the constant model and red is the trait independent model. So you can see some summary statistics can, in theory, reliably tell apart whether we have trait dependence or not, whereas others can tell apart whether we have two rate categories or whether everything is one constant rate. So we have to figure out which ones those are and kind of distinguish them from the ones that are a little less useful for our purpose. And of course, some of them will be redundant and some of them will actually be downright misleading. Now, another thing, and that's what I find specifically intriguing about this approach, is that we could maybe use those summary statistics to inform ourselves on how exactly a model is not adequate for certain data. What about the data? What about the model is it that causes it? So if we look at this example here, where we have a constant rate tree, state dependent tree, and we ran the model adequacy test on both of them. So this is the example of one summary statistic, and we can see, oh, okay, constant rate tree is here. This is the distribution of the simulated constant rate trees, and it falls within it. So it's adequate. State dependent is also adequate, as we said. Now here in this case, of course, we see that the constant rate model cannot adequately describe a state dependent process. So we can actually use this here, and this specific summary statistic, coalesce, refers to tree balance. So we can actually see, oh, the actual tree we're trying to analyze is different from what the model produces in this way and in this direction. So we can say like, oh, it creates a tree that is more imbalanced than what the model produces. So we can use that information to think about, well, what other models do we have? What models could make that kind of patterns? And either we can find models that exist, or we can, in the best case, even think about, well, what would a new model need to include to be able to create those patterns? And so that can be used, hopefully, as kind of a guide for the field as to where to develop next. Now, finally, there's obviously a lot of other possibilities here. So if we could actually use the summary statistics to characterize the models in terms of like, well, what kind of tree shapes do models lead to? Maybe we could revert that and look at a tree and its summary statistics and say, well, these kind of models create trees like that. So those should be our candidate models to start out with. And there's obviously questions about how we should really tune the adequacy test to our biological question, because, you know, cases can be different, and sometimes different summary statistics might be more important than others. And obviously, the hope is that there will be much more uses for this approach to solve all kinds of problems in our field. I think I've been kind of quick, because at this point I would like to thank a lot of people who helped me a lot with this. These are, you know, people of my actual lab, obviously, people of my host lab who have done a great job taking me in and been very welcoming and been very helpful, you know, not at least also with like comments on this talk, as well as very helpful people at Los Alamos, and a lot of people from back in Tennessee who had a lot of input on this here as well. And as well, thanks to NSF for funding me. Now, I think I ended up giving us a lot of time for questions, if you have any. And otherwise, I will, in any case, thank you for your attention.
Yeah, thanks, Orlando. We do have lots of time for questions, so please feel free to speak up, or you can put your question in the chat, and I will read it.
I have a question.
Mm-hmm.
Okay, so I'm not a phylogeneticist, so it's a naive question, which is great because it means that you get to show how smart you are. So at the end, you talked about looking at the kinds of distributions or patterns that a model produces, and then looking at a tree and starting with the model that gives you something that looks like that tree. That's kind of my interpretation of what you said. Isn't that circular? I'm trying to think of an analogy that kind of fits that.
I could see how it seems circular. I would, without thinking about it for half an hour right now, I think it would not necessarily be circular, because in an empirical case, we haven't made the tree using that model. We have made use of models to make the tree from, for example, genetic sequences, but those are different models. Of course, there's a whole rat tail of questions of like, well, how does our tree inference affect all of that, which is something we'd hopefully get into as well. But assuming that we get trees that are the result of a lot more and messier processes, I would think that it's not circular, because it really just points us at good candidates, which might still not be entirely the perfect fit. I'm not sure if that's a satisfying answer to that, but
I'm not sure either. I have to think.
It's probably worth thinking more about.
I probably have to think more than a half hour, though. Thank you for your answer.
Okay, let's have some more questions. sure there's some questions out there. Don't be shy.
Okay, I have a quick question. Great talk, Orlando. The PPS, what was that, posterior something, predictive simulation? Can that sort of approach be used to test for model adequacy for other processes, or is that like limited to diversification?
No, I mean, it is actually used in a lot of other fields as well. So I would generally say, if you have a model and you can both infer and simulate whatever data that model is supposed to deal with, then you can use that approach. So people have used it to, you know, from models that are involved in making trees, they have used them for models involved in trait evolution as well. And it doesn't need to be phylogenetic either way. It's like literally any model that you can simulate under can be used for this, which makes it really nice and flexible as well.
Sounds cool. Thanks, Orlando.
By the way, I'm also taking suggestions if you can't think of a question.
Okay, additional questions / suggestions from the audience?
I have a question, and it's really just reflects my confusion. So what is the difference between the disparity or the distance between a model and the truth and the concept of adequacy? Because I feel like this work addresses the question of like, could this model generate this data? Is it adequate to generate this data? And that's related to, but it's not exactly the same as saying how far away from the truth is this model?
That is very true. So I might have been mildly misleading with that figure that I've shown there. It is in fact more only related to it. It's not entirely the same. I mean, I would argue that if the model cannot make data that looks like our data, that probably does mean that we are far away from any kind of truth. Now, obviously, if it can create data that looks like our data, it doesn't mean that it has to actually be close to the truth, because you can get similar patterns from different processes, right? It just means that it could be closer to the truth, and it's definitely closer to the truth than the ones that are inadequate.
Yeah. Yes. I thought the first figure was brilliant in the sense of like, it just highlights this issue of we constantly, at least in my world, I'm constantly thinking about model selection and picking the best model and not being properly worried about, well, is how far away from the truth is the best model? Is it anywhere in the ballpark? And so, you know, I think it's a really important topic.
That is entirely the same thing in our field. I mean, I don't want to bash it too much, but you sometimes get the sense of like, we throw those models at our question and the best one we go with. And yeah, not a lot of checking to which extent that is actually feasible goes into that. I mean, now more so than in the past, but there was a certain trend of kind of like, do I find trait dependence for this trait? Yes, I do. Hooray.
Yeah, it also feels to me like it depends on what you want to do with the model, how consequential this is. If you want to take a model and make predictions, and the model can make good predictions about the future, about what strain of influenza will emerge next year, like I don't necessarily care too much about why it gets it right, if it gets it right.
Yes.
That's different than I want to draw inferences about what has happened in the past, and I don't have a time machine to go back. I need my model to get it right.
That is very true, yeah. It also goes beyond that, because we know that in any case, the models are simpler than reality, right? So we know that there have been a lot of things also happening apart from a model. So one of our thoughts was also that, you know, maybe we can use this to know whether our model gets the right answer to the question, even though it doesn't entirely match the data that we observe. For example, we might just want to know, does this trait influence diversification or does it not? Maybe there's other things going on that make the watermelon feel it, but maybe we can still know whether the answer is correct, even though some of the details are not. So that would be the hope to also kind of get at.
Yeah, super interesting. Thank you, Orlando. Great talk.
Okay, I think we still have time for another question if there's one floating around out there.
Hey, Orlando, I have a quick question for you. You guys can you hear me okay?
Yes.
Cool. That was great. Thank you for that talk. I'm curious about the Luca and Pennell paper that you mentioned and talked briefly about, and that sort of how model adequacy relates to this identifiability issue. And this is probably, you know, mathematically a little out of my realm, but I'm trying to think in terms of their results and your results and putting those two together. Maybe this is really obvious and I'm just not thinking clearly about it, but are they intimately tied together, or are there sort of nuanced ties between that identifiability and adequacy?
I'm gonna be honest, it is mathematically probably also a bit out of my realm at this point, and we've not really gotten to the point where we have tried to really address that issue with model adequacy. I think the hope would be that some of the hope would be that model adequacy could maybe rule out some of the alternative scenarios that Luca and Pennell say there are. So kind of maybe there is another model that, you know, has an alternative scenario going on that would fit this tree equally well as the model we started off with, but maybe that model would still make trees, if left to its own devices, make trees that look vastly different from what we're looking at. I'm not really sure yet whether that will work. There is absolutely the danger that model adequacy can only do very little to help with that, but I think it's definitely worth trying. It will not solve the whole issue raised by Luca and Pennell completely, but hopefully it could, give a contribution to that.
Cool. And so that's kind of where you were headed with those future directions at the end that Holly was asking about, in terms of trying to identify particular parameters that or summary statistics maybe that can help you key in on potentially where identifiability issues exist, as you know, as well as your adequacy stuff. Is that right?
I should try to follow that and be entirely sure that I got you right before I agree with you. I think yes. I'm not sure to which extent this. If the adequacy test will help with this, then the summary statistics themselves would probably help with it too. So we could use the summary statistics to tease out signatures of potential generating models. But yeah, I'm very much looking forward to get to that stage to see whether that works, or, I mean, there's a chance that, you know, if the other alternative scenarios fit the tree, they might fit it for a reason, and they might actually be adequate too. And different approaches might need to be taken. Like, I guess people are talking about taking into account more more biological knowledge on our data to kind of rule out some of the alternative models, because some of them might be biologically unrealistic. So that might help to like narrow down the space of alternatives. That I'm not sure the adequacy will help with directly, but they've already ruled out models that we don't even have to bother with. So
sure,
it helps a little bit.
Yeah, cool. Thanks. I think that helped me think about it. I'd like to talk with you more about this for sure.
I would look forward to that. Yeah.
Thanks.
There is a question from Jack Sullivan in the chat, which I will just read here. Jack says, my question follows from your last point to Craig. There's a difference between absolute goodness of fit of a model and that model's adequacy for making a particular inference. Have you tried to tailor your PPS analyses to particular common inferences?
I guess my question here would be what is meant by common interest. I think I know which direction the question is going, but I'm not entirely sure.
We still can't hear you. I think Jack's typing. I see typing motions happening. I was going to try to guess what you're going to say, Jack, but I'll just let you type it in.
I think he tried to say something earlier, but I think his microphone is like not really working. I saw him talk, but I didn't hear anything.
Okay. Go ahead, Luke. Right. Okay, great. Thanks, Jack. So one thing you might think about is like, you know, when people are fitting these sorts of models, what is the thing that they're really interested in? And what are the things that they consider sort of like nuisance parameters? And can we tailor the test statistics that we use to focus on the things that people really care about?
Yeah, I think that's a very good question, because that's part of what we hope we might get to. So I guess this goes in a similar direction as the question of maybe we get the actual rates wrong, but do we get the answer right? Right, so things like, oh, you know, there might be, I can always think about it as like data adequacy and question adequacy. Like we might have a tree that does have trait-dependent diversification, but there might also be trait variation going on, right? And so we might want to look for summary statistics that can catch the trait variation despite the time variation. I think in theory, it's reasonable to assume that we would find something like that. Obviously, there will be a gradient of like, well, depending how strong which of the processes is, one of them might just drown the other out. But that is very much part of our goals to kind of get at that. And there's definitely a lot more to get into in terms of how do we tune. I think that's what I meant with like one of my last points here, like how do we tune the adequacy test in a good way to test for what we actually want to know. I think the way to this will have to be to simulate a lot and start to kind of group our summary statistics in groups of, oh, what do they usually pick up? What do they have in common when they say yes, tell us yes or no? That was a bit of a ramble. I hope that kind of went in the direction of the question.
Yeah, I think so. And Jack has a follow-up comment in the chat, sort of talking about this analogous situation of divergence time estimation. If the clock model is wrong, it may still provide decent estimates of divergence times, even though, say, the R matrix can't be estimated accurately. And there's a thread in the literature that Jack is involved in that you could, I think, look to for inspiration in this particular way. So yeah, I think that's great. Thanks, Orlando. Are there more questions out there? We still have 3 minutes left.
I'll stop sharing so I can actually see the chat.
I will ask another question. Orlando, do you have a favorite summary statistic that you're hoping will be helpful, and or is there one that you think is super useless?
Ooh, I'm not entirely sure if I can come up with like the actual names right now. There are definitely some that seem to be very, for the models I've used so far, that seem to be very generally applicable. So definitely the whole, coalesce and the tree balance, it's a very, people have used, some of those that we're using, people have used a lot, and we kind of know what they give us, and it's good to see that they work. There's definitely some at this point which tell us nothing useful, and we just kind of leave them hang around because who knows, they might be useless for the models we're currently using, but maybe they suddenly are able to show us something in a model that we might include in the future, or maybe they suddenly turn out to be useful at like trees with very low species numbers or high numbers, or if the traits are very unevenly distributed, or maybe they suddenly become important for if we use like multiple trait states all of a sudden. So yeah, I'm definitely fond of the two ones that I've shown that can kind of, one figures out whether we have one or two rate categories, and one of them figures out whether we have trait dependence or not. So the fact that they are, I mean, those cases were in like a bunch of simulated trees that we simulated to be different. So the fact that they can pick out both of those aspects separately kind of makes me kind of hopeful about the whole thing.
Great question, Brianna.
Thanks, Orlando, for the hope.
So I think that's all the time that we have, but I will encourage people to get in touch with Orlando. It's a little bit hard to take advantage of the magic of IBEST in the pandemic era because we don't know who's here. And so this is a great person who's here that I'm sure would love to talk to all of you in more detail about these things. So thanks a lot, Orlando.
Well, thanks a lot.